Everybody, welcome back. This is our next set of tutorials for our Advanced Media Skills class. This is dealing primarily with 3D printing, and it's going to be a two-parter as well. The first part, we're going to look at modeling for 3D printing, some particular issues you can run into, ways to analyze your geometry, make sure that it's kosher for the process, and a potential modeling workflow that you may want to use. And then the second set, or the second video, we're going to look at exporting geometry and doing a setup in slicing software, specifically in Prusa Slicer. So let's get into it. So I'm going to bring up my Rhino. All right, so as we said last time, Rhino is a surface 3D modeler. And what that really means is that we are using surfaces to build objects, digital objects. Usually, if we are, trying to get an idea out into model space, we are, putting stuff together rather haphazardly. To convey a particular idea. And then if we need to, we go deeper, rebuild, remodel to get, something a little bit more polished out. Okay. Now, usually, if we're doing something like that, we're not really worrying about particular downstream processes, like what we're going to use the geometry for. Okay. Well, we are now leaving that particular idea behind. We are shifting gears into, we want to model something specifically for 3D printing. Okay. Now this brings up the notion that there are essentially two types of 3D models that we would be making potentially. The first is our design model, which is, again, like I said, something where we are not really worrying about what we're going to use it for. We're throwing stuff together, cutting stuff apart to convey the idea. The second type of model is the production model. This is geometry that is tailored, that is tuned for very specific downstream processes: 3D printing, laser cutting, CNC machining, interfacing with other specific types of software. Process is now being inputted into the geometry. All right, that's the main change. That's the main focus that we want to think about. Now, if I just make a piece of geometry, and let's actually, before we do that, make a new layer, and let's make this. Let's make this pink. All right, and I just make a box. Quick and easy. No real dimension. This is a simple solid. All right. It is composed of 6 sides. 1, 2, 3, 4, 5, 6. And when I select this, it is, if we look down here, one closed extrusion added to selection. That means that this is a closed polysurface. Okay, now we need a closed, specifically for 3D printing, we need a closed polysurface for a very specific reason. Whenever we are taking our geometry and exporting it into our slicing software, doesn't matter which one. Essentially, what that software is doing is creating layers. Right, from the bottom all the way to the top, however many layers it needs. Now, essentially, what that slicing software is saying is anything that is inside the geometry is what gets outputted for 3D printing. And anything that is outside that geometry doesn't get outputted for 3D printing. Right? Inside, outside, a very unambiguous relationship. And the way to do that is to have a closed poly surface. Okay, if it's an open polysurface that is not what we would call watertight. Think of like a crack in a glass. You know, you pour a nice hot coffee into a cracked coffee mug, and it starts dripping onto your hand, and it feels very uncomfortable. You know, that's no good. That's not watertight anymore. Now, usually when we're modeling, especially if we're doing just like trying to output a design, we're not worrying about water tightness or creating a closed polysurface. Usually that is not a problem. But as soon as we say, I need to 3D print this, okay, the 3D printing process is now being integrated into the geometry that we're creating. Okay, so the name of the game is a closed polysurface. Now, if we're simply doing extrusions, like if I make a rectangle and I go to side view and I make a piece of geometry, go back to perspective, surface, extrude curve, along curve. That's the curve we want to extrude. This is the path we want it to take. All right, that works. All right. Technically, this is 4 surfaces. All right, 1, 2, 3, 4. This is not a closed polysurface. We need this to be a closed polysurface. If we select it down here, 1 open polysurface added to selection. Okay. Now, there's various different ways we can make this closed. If I wanted to add a little pizzazz, you know, let's make a little spline action here. Turn off ortho. And I'm going to say disable, so I don't snap to anything. That. Perspective. All right, let's take this, extrude. All right, trim. I'm going to select everything. Trim that. Trim that. Actually, no, I'm sorry. We don't want to select the curves. Trim 1, 2, 3. Come on. All right. There we go. There we go. All right. Get rid of that. All right. Let's get rid of that. Let's get rid of that. All right. If I select all this, 2 surfaces, 1 polysurface added to selection. All right, let's select everything. Where it's going to say join. 3 surfaces or polysurfaces joined into 1 closed polysurface. Boom. This is in fact 3D printable. Now this is very, very simple. All right. Now, and this is a singular object. Let's add a little bit more complexity. Let's turn on example 1. Get rid of that. Let's zoom. Okay. Let's say this is the thing I want to 3D print. Okay. Right now, these are multiple singular objects, closed objects. All right. We want to 3D print this. Okay. Well, we do not want these to be singular surface or singular pieces. All right. What we want is to be able to select, is to join essentially everything together. Now, if we zoom in here, one of the things we'll notice is that the geometry is overlapping, all right, but there's geometry of one going into the other, and vice versa. All right. Now, if these were joined together, then essentially the space inside this object would be able to flow into the space into the next object. Right? Now, the way we can do that is relatively easy. Since these are closed polysurfaces, what we're going to do is a Boolean union. Now, Boolean operations are operations that can work, that only really work on solids, on closed polysurfaces, let's say. So I'm going to say Boolean union, right? Select surfaces of polysurface union. Select 1, 2, spacebar. All right, now the overlap that we saw is now gone. And if we zoom in to this, into that space, right, the space inside here is flowing into the space inside here. All right, and that's awesome. Now, we zoom out. All right, these two select. They are joined together as one closed polysurfaces. Now, essentially everything else needs to be the same. Now, what we're going to do is we're going to select. We're going to try, see if this works. We're going to select everything. And we are going to say Boolean union again. Cross our fingers. Okay. And fantastic. When I select it, everything selects. When I zoom in and take a look, all the overlapping pieces are gone. This is able to be 3D printed. We have a closed polysurface and have taken care of all the issues that we would need to take care of for 3D printing. Now, the reason this is important, if I just step back, this overlapping geometry is potentially a major issue. Okay, I know several of our 3D printers in the RPC, this would be a major issue. I know 1 or 2 3D printers that it's not an issue, but the basic principle, the rule of thumb, is that this sort of condition, this overlapping geometry, is always going to potentially be an issue. Now, the reason it's an issue is it's an interpretation issue. Some softwares interpret this as void here in this overlapping area. So it's inside on this one, it's inside on this one, and it's outside where the overlap is. Now, if you want these two parts to be 3D printed where they're actually attached, the fact that the software sees this as not inside is problematic. Another potential issue is certain softwares will read this as double density. Okay, you're putting out a certain amount of material here, you're putting out a certain amount of material here. In this overlapping area, it puts out double the amount. This is a real big issue on extrusion 3D printers. If it puts out too much filament, it'll clog, it will potentially rip your object off of the build plates, chaos ensues, everybody has a bad time, tears shed, curses levied against the 3D printing gods. It's horrible. It's absolutely horrible. Right? But if we understand that, you know, if we are starting with closed polysurfaces, sometimes it is as simple as select Boolean union, and boom. There you go. All right, now let's add a little bit more complexity. Instead of closed polysurfaces, let's go to example 2. Same geometry, except this has been exploded into individual surfaces. Okay, now one method we could do in this particular scenario is we could select everything, say join, 128 surfaces or polysurfaces join into 16 closed polysurfaces. Perfect. Then we can Boolean union. But let's assume that for some reason that they don't join into closed polysurfaces, just for the sake of argument. What we would have to do is a little bit more of a brute force method. Okay, what we would have to do is actually trim the geometry inside of here and inside of here so that we get that flow from one to the other. So in theory, it's as simple as, let's select this, trim, and then trim that surface, and 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 that surface. All right. And then we would have to do the same thing for this. Okay. Trim, 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 and trim again. Okay. And keep doing that. Oops. And hope that you don't make a mistake like I did just there. Not that big of a deal. We'll back step, there. Okay. Now, this is rather intensive, and it requires a certain amount of patience, but it is in fact a workable method. Now, the obvious issue is the more complex your geometry, the longer it's going to take to do it. Okay, now this is why, especially new modelers, I would say, kind of default to the extrusion method. Okay, you're starting with solids. You have a much wider range of easy, simple tools and workflows to kind of get everything done. But as soon as we start adding complexity, things start getting really, really weird really fast. Now, I'm going to cheat a little to showcase a very particular issue that you may run into. So I'm going to select all of these and say join. Okay, so that's all. So these are all closed. I'm going to select all of these, and I'm going to say Boolean union. Okay, but I haven't done this one yet. Okay, for a very particular reason. I'm going to select this, say trim, 1, 2, wait, shoot. Let's do this. We're going to select this, we're going to trim that back first. And we're going to select this, and we're going to trim that. Oops, not that. Oops, sorry. Explode. All right, individual surfaces. There we go. Okay. That. Trim that surface, and that surface, and that surface. Okay, but oh no, I forgot one, and I didn't notice. Select everything, join. 9 surfaces or poly surfaces join into one open poly surface. Uh-oh, that's a problem. Now, what do we do? Well, there is a handy-dandy tool, a handy-dandy method we can use to figure that out. Okay, so if we're squirreling all around and we don't know where the problem is, where the open part of it is, there is a method to check it. Okay, so we're going to come up to Analyze, come down to Edge Tools, and we're going to say Show Edges. Now it'll say select surfaces, poly surfaces, or meshes for edge display. We're going to select that. And we're going to say spacebar. Found 258 edges total. That's not a problem. 3 naked edges. That's a problem. No non-manifold edges. That's good. So in order for a poly surface to be a closed poly surface, a watertight poly surface, we need It doesn't matter how many edges you have, but we need to have 0 naked edges and 0 non-manifold edges. Now, we have 0 non-manifold edges, but we have 3 naked edges. Now, we want to make sure that this edge color that we see right here is a different color from the color of the layer that we're working on, because if we zoom around, oh wait, what is that? It shows us where zoom in, where that naked edge is. Okay, so if we select this, okay, it's joined all together. So what we're going to do is we're going to select, we're going to say explode. All right. Now, okay, so this portion of the edge of a surface is extending into the inside of this. That's the problem. We need to get rid of this. Now, there's lots of ways we could do that. The one we're going to try first is we're going to say trim, select cutting objects. We want this surface, spacebar, select object to trim. It's going to be that. Okay, so we got rid of that. Now we're going to zoom out, say join. 128 surfaces or poly surfaces joined into one closed poly surface. Fantastic. This is now 3D printable. So a naked edge is essentially a surface that's not joined, the edges are not joined to anything else. So technically speaking, if I type in plane, just make a plane, this is just a surface. It has 0 thickness. Okay. This is the problem. Planes that have 0 thicknesses, okay, when they're interacting with other surfaces, that's where you start to get the naked edge. Okay, and that's what we want to try to avoid. Now, the way we would avoid this is if we simply say extrude. Actually, no. Let's do this. Let's say offset. Offset surface. Select that. Distance, that's a 1/16 of an inch. Okay, zoom in. All right. Actually, let's try that one more time. Offset. And let's look at some of the options here. Zoom down a little bit. Cap. Flat. Sorry. Oops. One more time. Offset. Surface. There we go. Select surfaces. Solid. Boom. Okay. Now we've got 5 more surfaces to describe an enclosed space. Okay. So, naked edges. They're a problem. And the edge analyze tool is what we would use to find the areas that would be problematic. Okay. Now, a naked edge, turn on example 3. Okay. Let's say we've got, these are 2 extrusions. All right, and they are sharing this edge. If I go to say join, select this and this, one more time, this and this, it's not going to join together. Okay, I'm sorry. Let's step back a little bit. Non-manifold edges. They are edges where multiple surfaces are coming in together. And we don't know how, or the software has trouble interpreting essentially how areas kind of flow against each other. Okay, now, the fact that This is selecting separately from this, means that this is not joined together. Okay, so technically this is not a naked edge. But if we made, so I'll disable, some sort of base, right? And we say copy, move that up to there. Okay. So this is a 1 surface, 2 surface, 3 surface, 4 surface. If we simply do the Boolean union, okay, join that together. Oh, Boolean union failed. Interesting. Okay. Let's just get rid of that for the time being. And if we select this, this is a 1 open poly surface, not 3D printable. Now we have these little things here and these little things here. If we add this there we go. Okay. Now, the problem I had was I didn't have non-manifold edges selected. Okay, actually, let's do this from the top. Analyze, mask properties, edge tools, show edges, select surfaces or poly surfaces or meshes for edge display. We'll select that. Found 35 edges total, no naked edges, that's good, 1 non-manifold edge, that's bad. Okay, now this is slightly more complex to deal with than the naked edge. Because the question is, how do we want to make the interpretation? Okay, now, if we were to 3D print this, or attempt to 3D print this, the biggest issue is that this and this are not going to be connected together. And the reason they're not going to be connected together is because they do not flow technically from this space to this space this way. Okay. Now they flow from down, and around and back up, but not from here to here. Okay. This really requires a different method, a different approach to our modeling in order to fix this. So let's do this. I'm going to make a new layer, and I'm going to make this cyan. I'm going to say rectangle. And so what I'm going to do is I'm actually going to rebuild this from scratch. Okay, this is my design model. It got the idea across. All right, now it needs to be more specific to the process I'm looking to put out. All right, so the method I'm going to fix this is I'm going to rebuild it and model it slightly differently to take into account to this naked edge issue. Okay, so the method, the way I'm going to do that is I'm going to say rectangle, and I'm going to go from there to there, and I'm going to go from there to there, and I'm also going to go from there to there, and I'm also going to go from there to there. Okay, I'm going to turn this off. All right, now there's, I'll take this, and I'm actually going to make a copy, and I'm going to turn ortho back on. Okay, now I'm going to take this and I'm going to explode it. Okay. Now, this is a 0 right here. All right. Now, the main way to fix this is to make it not a 0. Anything above 0 is still technically not 0. So I'm going to say fillet. Not fillet edge, but just fillet. That's our 2D geometry. And I'm going to give myself a radius. Let's say 0.1. A little bit less than an eighth of an inch. And I'm going to say this and this. And I'm going to say this and this. Okay. And that's it. All right, if I select all this, I say join. 6 curves join in one closed curve. Perfect. I can say extrude. And I'll extrude as a solid up to there. All right, I can extrude that up to there. Boolean union. 1, 2. All right, let's try this one more time. Select one closed poly surface, add to selection. Fantastic. But let's do the formal analysis. Analyze, edge tools, show edges, select surfaces. 42 edges found total. No naked edges, no non-manifold edges. Boom. This is 3D printable. All right, now, essentially what we did is we added thickness here, okay, to make it essentially one discrete object from here to here. All right, now, the other method is if we do, I'm sorry, let's get out of that. We'll say fillet just for the curves. Let's do this and this. And this and this, and we join. All right, and we select this. Oh, okay. Select this, extrude that up there as solid. Take this, extrude that up there as solid. Take this, extrude that up to there as solid. Boolean union. 1, 2, 3. Now that's 3D printable. Now the question you may ask yourself is, which one is better? They're neither better or worse than each other. They are different methods to overcome an issue, specifically an issue that we find in 3D printing. Okay, non-manifold edges are bad, so we have to get rid of them somehow. So we have to find a way to get rid of it by either joining things together so that they aren't two discrete objects, like in this, or making two discrete objects, like in this. Okay. Basically, that's it. If you can create a closed poly surface with no naked edges, with no non-manifold edges, then you are good to go for 3D printing. Okay. So what we're going to do is next is I'm going to show an example that an example of potentially of what you may be doing, could be doing for our project 2. And what we're going to be doing, what you're going to be doing, is going to the art museum, finding a painting, and making abstractions, 3D abstractions from those essentially 2D representations. Okay. Now, I'm going to do that. All right. Now, the painting that I chose, which is kind of one of my favorites, is Marcel Duchamp's New Descending Staircase, specifically a New Descending a Staircase number 2. Okay, This is actually the later version. It's the one we typically think about, but this was done in 1912. New Descending a Staircase number 1. This is what that looks like. Now, personally, I like number 2 because it has a little bit more geometry, a little bit more perceived or prescribed motion, and the more kind of prescribed depth. This, although beautiful, is kind of flat, whereas this has, even though it is essentially a 2D surface, a lot of implied visual depth, which I find interesting. Now, a little bit of history. In the 1880s, 1890s, when photography was really starting to come about, several people in France were doing what's called chronography photographs. And those, sorry, kind of look like this. This is, I'm going to butcher his name, so Jules Marais. This is done in 1883. This is essentially a single or a multiple exposure photograph of him wearing a very specific suit, walking across the screen, across the field of vision, and essentially in a very special suit that showcases where kind of the joints are, showcasing the motion of walking, the motion of from one side to the other side. There were several people doing these sorts of photographs. This was one done by him in 1890, a multiple exposure. You know, visually, this is really interesting. This is brand spanking new. Nobody was doing anything like this. This was one of the things that was inspiring Duchamp to make his painting. So he made the painting, sent it over to New York, and there was instant uproar. This is blasphemy, they said. It's completely different, completely outside the norm. And at the time, you know, people really hated it. Tried to keep him from showing this work. And made some very rude cartoons kind of lambasting the art that he was making. Now, a little over 100 years later, this Duchamp's New Descending Staircase is regarded as a modernist masterpiece. And it has inspired a whole host of other artists to kind of explore, to utilize in new and different ways. One of those is from my favorite comic strip, Calvin and Hobbes. These are two riffs of Watterson looking at integrating what New Descending Staircase was doing. Very tongue-in-cheek. This is my childhood. I love Calvin and Hobbes. All right. But, so this was 95. This one was 95. This one was 93, if I remember correctly. All right. So, with this in mind, okay, this is what I am going to abstract. This is the painting that I'm going to use. Now, I've done a whole series of iterations before this, but I'm going to showcase how I am going to build the model for this. So I'm going to turn on my working lines layer. I'm going to turn off this. I didn't import any geometry. All right, I'm just building this from what I see in my mind's eye. And the end product, just to give you a preview, you know, it's very simple. Yours are probably going to be much more complex, but essentially implied rotation and depth. Those were the two real key takeaways I got from that painting. All right, and this is just my method, very simple method, very direct method to kind of showcase that. All right, now it's the same object, modeled once and then copied, and then rotated. All right, So this is the geometry I made to do this. All right, so I have a cross section, I have this piece for the curve, and I have two cap geometries. All right, so what I'm going to do is I'm going to say revolve. Select curves and revolve. I'm going to select that. Start a revolve axis. I'm going to snap to the center of this curve here. Kind of go out that way. Now, instead of making the full 360, I'm going to say this is my start point, and this is my end point. Okay, so that was step number one. All right, I'm going to take this and I'm going to put it onto this layer. Okay. All right, now I need to cap this. So I'm going to take this and I'm going to take this and I'm going to say extrude curve, and I'm going to go to the top, and that looks okay. Go back to perspective. Okay, I'm going to select the extrusion. I'm going to select the extrusion. I'm going to put that on my layer. All right, I'm going to turn off my working lines, and I'm going to say trim, and I'm going to say all this is my cutting objects, and I'm going to say trim that, that. Oh wait, that's not working. I wasn't paying attention. Okay, we see here the fact that that doesn't fully encompass, that's problematic. All right, so let's go back, and I'm just going to shift these over. Go back to the top view. All right, we can see that right there. Okay, perspective, trim, and we're going to say all this again. We'll say 1, 2, 3, 4. All right. Then if we join this together, 3 surfaces or poly surfaces join into one closed poly surface. Fantastic. But let's say, for the sake of argument, that I was able to get the bottom one to trim, or somehow, we won't say how, somehow I wasn't paying attention, and or I went to go rebuild something, and I say trim, okay, and I say join. All right, checking down here, 3 surfaces or poly surfaces joined into one open poly surface. Uh-oh, that's problematic. Now, we all know where it is, right, because I specifically did it this way. But if we couldn't visually see, right, analyze, edge tools, show edges, select, total 9 edges found, 2 naked edges, and 0 no non-manifold edges. All right. So because we see there we have 2 naked edges, we're going to say select naked edges. All right, and it shows us where this is. Now, how do we fix this? Let's try cap. Let's see if that works. Okay, unable to cap. Yeah, okay. No planar edges. All right, so that's no good. Let's see. Maybe we can kind of stitch it together. All right, and then join. 2 surfaces or poly surfaces joined to one closed poly surface. That technically works. Now, I think this is probably going to give us issues further down the line. So the way that we want to fix this, delete, is I'm going to re-extrude a whole new thing. Make sure that we overlap. And say trim, use this, and this. Okay. Now we join together. Right. All right. Selecting this object, one closed poly surface added selection. Fantastic. All right. And just to be safe, analyze, edge tools, show edges. 6 edges total, no naked edges, no non-manifold edges. Fantastic. This is what we're going to use. We'll turn this off. All right, so this is a little sharp for my liking. So I'm going to kind of soften this. So I'm going to say fillet edge. And I'm going to say for the radius 0.1. I'm actually not modeling this to any particular scale, just kind of visually. We'll worry about scale later. So I'm going to do that, that. All right. And this is still a closed poly surface. All right, now I'm going to take this. Now, because this is a closed poly surface, moving forward, we can use a lot of our solid-based commands, like our Boolean commands. And what we're going to do is we're going to say copy. Let's move this, actually we're going to move it to a top view. This will help. And let's say 1 inch. Then we'll say 2 inch, and then 3 inch, and then 4 inch, and then 5 inch, and then 6 inch. Okay. Now, back to perspective. So we got these pieces right here. All right, now for this, all right, I purposefully modeled at the origin. And I did that because it would allow me to do the next very, very easily. So I'm going to go to front. We're going to say rotate. Center of rotation, we're just going to say 0. All right, and we're going to rotate, let's do 30 degrees. Okay, now I'm actually going to split the viewport. Right? And so I'm going to deselect all those and then reselect everyone except one of them. And then it's going to be a lot of repeating. So rotate, starting from 0, and we'll say 30 again. And we'll select the next ones, starting from 0, 30. All right, one less. Rotate, starting from 0, 30. Just keep going around. Oops, 0, 30. And the last one. 0, 30. All right. So now we have recreated the thing. Now, as a design idea, this is probably as far as I would need to take it. It kind of conveys what I think. Now, we're going to shift gears. We're going to say, well, this is fine as a design. Now we need to make it 3D printable. I'm going to hide this. So, technically, currently, these are 4, 5, 6, 7 separate objects. but they're all closed objects. So what we're going to do is we're going to select all of these, and let's try Boolean union. All right, ooh, that looks like that worked quite nicely. All right, one closed poly surface added to selection. Glorious. Now, if we go to just to triple check, analyze, edge tools, show edges, select surfaces, 174 edges total, no naked edges, no non-manifold edges. This is 3D printable as it stands. But I want to add a little bit more pizzazz to kind of showcase or show how kind of one flows into the other, into the other, into the other. I'm going to see if I can't kind of soften this transition. This is fairly sharp in the inverse. So let's say fillet edge. Let's say 0.1 as a start point. This is going to be a little exploratory. Select that. All right, well, it did the thing, but we'll notice that's problematic. And that's problematic. So 0.1 is a little too big. So let's step back. And let's say fillet edge. All right, let's just have that 0.05, which is a little bit less than a 16th. Select our, oh wait, sorry, more time. 0.05. Oops. There we go. Select that. All right. So it did fill it. It is still closed. Now, let's see if we can't make that a little bigger. All right. So if 0.1 is too big and 0.05 is just slightly too small, let's make it 0.075. Let's see what we say. All right. 0.075 is too big. All right. So let's do 0.06. Oh, yeah. All right. So that works right there. And that works right there, which is nice, but it would be visually more interesting if the fillet was bigger here and bigger here. So let's try that. So step back, fillet edge. Let's select the edge that we want. Okay, now we're going to get tricky. We're going to say add a handle. Actually, no. If we zoom in here, we can actually, so this is the fillet handle. And we can actually change this on the fly if we wanted to. But we don't. Well, not yet. Okay. But we can also move this. So if we take this and click and drag, put one right down there. Okay. And then if we say add handle, we can actually put one up in here. And then I'm going to put one there. And I'm going to put one there. Okay. Now I want this to be a 0.06. I want this to be a 0.06. I want this to be bigger. So let's click. We can actually type in a number. So I'm going to say 0.25. Let's try that. And 0.25. All right. Then cross our fingers. Oh, fantastic. That's exactly what we want. So I got a bigger fillet out here where I want it, a smaller fillet in here where I want it. This edge isn't overlapping this, and it's a closed poly surface. So what we're going to do is we're going to replicate this for all the rest of these. Now, I've said this before, but the fact that Rhino is a surface model allows us to do stuff like this so much easier than a solids modeler. Now, there is a real issue though. Okay? The more complex geometry that we model, the harder it is to maintain a closed poly surface, a watertight model, specifically for 3D printing. It is not impossible. It is definitely not impossible. It is just much, much more challenging. Because it really comes down to how you end up modeling the geometry. A lot of times not quite, Nick. A lot of times, whenever you get to this point where you're remodeling geometry for your downstream processes, you have to try several different methods in order to find a method that does the thing that you want and maintains the geometry requirements that you desire. There is no one way of doing it. And the more complex that you want to make your geometry, the more complex it is to maintain that relationship. But you could also say that's where most of the fun is as well, in certain situations. 0.25. 0.25. So these pieces are actually starting to blend visually more together, which is what I want. Edge, select that. Now, this is fairly redundant. We're doing the same thing over and over again, but unfortunately, this is kind of the only real way to do it. There's no way we can kind of pre-build this before we do the copies and before we do the boolean, because it's how the geometries overlap, which allows us to do these sorts of visuals. So this is always going to be a secondary process. Keep on trucking. Keep on trucking. Handle. Now, I will admit, I'm not being very careful where specifically I'm putting these handles. If it did matter, then we would probably want to give ourselves some secondary geometry that we can copy and rotate with the other geometry to make sure that we're being consistent. As long as it's close, it's good enough for what we're doing currently. And more importantly, that it still maintains our watertight condition. Right? So when I do this, I select one closed poly surface added. Perfect. Now, if that changed from closed to open, right, then there would be cause for concern. So then go back and dive in to figure out why we went from closed to open, and that's part of the detective process. Add a handle. Add a handle there. We need to move that over to here. We'll add a handle. And trying to find the right view to see this in. There we go. Say there. And we'll say there. Change this from 0.06 to 0.25. 0.25. And the last one. All right, now this is probably, again, just like with our telephone receiver example, this looks like a linear process. You do this, then you do this, then you do this, then you do this. The only reason it looks that way is because I went through and figured out, not good enough, change it around a little more, figured out essentially how to do this, okay? So that's why it looks like a linear thing. But before this, there was a lot of back and forth, testing things, figuring out what was working, what wasn't working, to get an example that, for all intents and purposes, that looks like I know what I'm doing. All right, at the very beginning of this, it was very, very exploratory. This model is actually iteration number 3. 0.25, 0.25. All right. All right. Now let's change the view. Let's say rendered. What does that look like? Yeah. I think this is going to work for what we want to do. Actually, let's try the artistic. Hopefully it doesn't crash my computer. Actually, there we go. Actually, let's save. Again, shoot, I just went the entire time without saving once. Don't do that. Don't do that at all. All right, this is perfect. All right, this is exactly what we want. So we now have a model that's ready for 3D printing. In our next video, we're going to cover exporting this and our 3D printing setup. So I will see you in the next one. Cheers.